I'm Dave. This is Zia. We are principal engineers in the Intel compiler team, and we're going to be talking to you today about the work we've been doing to improve LLVM generated code size for x86 processors. These days, we have powerful computers with large, inexpensive storage devices, so tuning compilers for minimal code size is something that often gets ignored. Or if not completely ignored, it takes a back seat to optimizing for speed. Well, there are some environments where code size is still an important design objective, if not the most important design objective. And in these environments, saving on code size can translate directly into dollars or euros. Or maybe you're interested in code size just because you're old-fashioned and you still like to carry your programs around on these babies. You know, to each his own. Well, our interest in code size comes from the work that we've been doing to target LLVM for the Intel Quark microcontroller D2000. Now, the D2000 has a fixed and limited amount of physical memory on die, so naturally, code size is an important design goal. Now, just to set the expectations early, this is not a presentation that's predominantly about Quark or microcontrollers. The Quark is an x86 part, and most of the code size optimization work that we've been doing applies equally to all x86 parts. But just to give you some context to understand the type of code that we're looking at and optimizing, it's useful to know that the Quark is a 32-bit part with a Pentium instruction set minus the x87 native floating point support. So what we're talking about here is very generic, general-purpose x86 integer code. So how did LLVM code size look at the start of this project? Well, our basis for comparison is going to be GCC 493. And if you take that compiler and compile all the C and C++ benchmarks in SPEC 2000, add up all the code section sizes and all of the object files, what you get is something just over 3 megabytes. Now, before I show you the comparative data for LLVM, I just want to say a few words about how that data was measured. So we started this project roughly a year ago, and we're still in the process of finalizing some of our patches and getting them committed to trunk. So it wouldn't be an accurate reflection of our work to compare a snapshot of LLVM from a year ago to a snapshot today, both because our work still hasn't been all committed, and because of all the stuff that has gone into LLVM in that time frame. So what we did instead was take a recent snapshot of LLVM trunk, add in the few remaining things that we haven't yet committed, and also add experimental controls for all of the optimization work that we did. So with that in mind, if you take that recent snapshot of LLVM trunk, subtract out all of our optimizations, and run the same experiment, what you get is code size that's roughly 12% larger than GCC. Now, what we'll be talking about for the remainder of this presentation is how we took that 12% gap and reduced it by 11% to near parity with GCC. We'll talk about the methodology that we used. We'll talk about the individual optimizations that contributed to this improvement. We will give a more complete picture of the results. And we'll give a few directions for future x86 code size work. And before I go on, I just want to point out that all those experimental changes that I was talking about to LLVM trunk, those are posted publicly in a Fabricator review, along with the instructions about what exactly specifically we did in our experiments. And a link to that Fabricator review is in the backup foils of this presentation. So the code size team consisted of 5 engineers, Zia and myself, Michael Cooperstein, Andrei Turetsky, and Anton Nadolsky. And the first question this team had to deal with was what metric to use to evaluate code size. Now, in the microcontroller segment, the benchmarks that are typically used to evaluate device performance, they tend to be really small. And we were concerned that if we limited our focus to just those benchmarks, it wouldn't really be representative of all the type of code that you might be running on the microcontroller. So we wanted something with a bit more breadth, and that's why we chose SPEC 2000. Once we had our metric, the primary technique that we used to find our code size optimization opportunities was gap analysis. So we would take a benchmark, compile it both with GCC and clang, and then look at those functions or modules where the clang-generated code size was significantly larger than the GCC-generated code size. And we found a great many optimization opportunities this way. And for each one, we would evaluate the code size savings potential, and we chose to carry through to implementation those optimizations where we thought there'd be good return on investment. And also at this point, we would make a code size performance trade-off determination to decide whether something was appropriate for O2 versus OS or OZ. So over the course of the next few foils, what we'll do is go through and look at some of the individual opportunities that we did decide to carry through to implementation. And for each of those findings, or if you prefer range-based for loops, since that seems to be the trend in LLVM these days, for each finding, we will explain the opportunity and give an example. We'll report the improvement on our code size metric, and we'll give you the status of where the fix is in LLVM trunk. We'll start with a very simple one. In the x86 architecture, if you want to compare an immediate value, a small immediate value with memory in one instruction, you have two choices. You can use the 83 opcode family instruction, which encodes the immediate in 1 byte, or you can use the 81 opcode family of instruction that encodes the immediate in 4 bytes. Now, there's virtually no good reason to use the instruction that encodes the immediate in 4 bytes, but there were some conditions under which LLVM was being conservative. And our fix in this case was just to eliminate that conservatism. And note that this idea doesn't just apply to compare. It applies to all of the mop-mem instructions like add immediate with memory. It just turns out that compare is by far the most predominant of this type of instruction. Our fix for this led to a 0.22% code size reduction. Now, that might not sound like a lot, but what it amounts to is about 7,000 bytes out of the 3 megabytes that we're talking about here. And in this case, the savings is coming virtually for free. There's virtually no downside to using the more efficient encoding here. And this fix has been committed to trunk and has been there for quite some time. The next optimization is similar in that it's an improvement with relatively no downside. As I said earlier, Quark has no native floating point instruction support. So all floating point operations have to be implemented via a software floating point emulation library. And we found that LLVM in some cases was making inefficient use of that library for some floating point comparisons. So consider this FCMP. The compare condition here is unordered less than or equal. Now, that is not something that maps directly to C. If you write less than or equal in C, what you get is an ordered less than or equal comparison. And the difference is that with an ordered comparison, if you have a NaN operand, the return value is false. And in an unordered comparison, a NaN operand will result in a return value of true. So the way this condition comes about in LLVM is that there are some optimizations that will invert the compare condition. And unordered less than or equal is the inverse of ordered greater than. So what LLVM was doing with these unordered comparisons, it was making two calls into the soft-float library. So one call to the ordered less than or equal to function, and a second separate call to specifically check for NaN. Now, the more efficient way of doing it is to make one call to the ordered greater than function, and then effectively check the return value for false. So again, there's virtually no downside to doing this. And this is both a code size and a performance fix, so something that's appropriate for O2. Our fix for this affects all targets, not just Quark, not just x86, but all targets that use software floating point emulation. We found that this gave a significant code size reduction, and this fix has also been in LLVM trunk for a while. The next fix relates to a performance optimization that was checked into LLVM a few years ago. The purpose of this fix was to eliminate processor stalls caused by partial register writes. So consider this example. This is a load instruction that's taking 8 bits from memory and storing an AL. AL is an alias for the lower 8 bits of a larger 32-bit register, EAX. Internally, what the processor has to do with this instruction is take these 8 bits that are coming from memory and merge them in with the previous value of the upper 24 bits of EAX. Different processors deal with this merging behavior differently, but the nasty effect in most modern high-performance out-of-order processors is that this load will have a dependence on the previous value of EAX. We like to call this a false dependence because typically the software doesn't even care about these upper 24 bits. It's only going to use the loaded 8 bits in any meaningful way anyway, but the machine doesn't know that. So it still has to wait on the previous value of EAX being available. These false dependencies can be especially costly when the defining instruction for EAX is some very high latency operation like an integer divide. Well, what was done in LLVM to deal with this problem was to take 8 and 16-bit integer comparison instructions and unconditionally promote them up to 32 bits. So this is what I would call a pragmatic fix. It will certainly eliminate this problem to some extent, and I'm sure it fixed the problem at hand, but it did come with a rather hefty code size cost. We found that by fully reverting this performance fix, it improved code size by almost 0.8%. Now, here's an example just to illustrate the effect here. The code on the left is code that you get for a very simple signed char comparison with the current version of LLVM. What you have here is 2 8 to 30-bit sign extending load instructions followed by a 32-bit comparison. If you revert the performance fix, you get the code in the middle. You can see it's much more compact, right? It's 8 bytes versus 12. And what it consists of is an 8-bit load into AL, followed by a fuse compare memory with register. Now, this code does still have the performance problem that I was talking about, right? So what we ideally want is something more like what's on the right. Here we have a fully extending load, so we've eliminated the partial register write and addressed the performance problem, but we've left the comparison as an 8-bit comparison to preserve the ability to fuse load operands that are coming from memory. So this costs us 1 byte over the more compact code, but we find this to be a good code size versus performance trade-off. And we're currently working on an optimization that will allow LLVM to more consistently give us the code like what's on the right. And an initial version of this optimization has already been checked into trunk. It's not yet enabled by default, but our plan is to tune that optimization, get it enabled by default so that ultimately we can revert the original performance fix. So the last optimization I'll be talking about before I turn the mic over to Zia is tuning loop rotation for code size. So you can see here a very simple C for loop that runs from 0 to n with a stride of 1. The sort of straightforward way of generating code for this is to first generate the initialization code, then to have the loop termination check at the top of the loop and break out if it fails, or I guess if it succeeds, then have the loop body, then the IV increment code and an unconditional branch back up to the top of the loop. Well, what loop rotation tries to do is optimize the branch structure of this loop by moving that loop termination check down to the bottom of the loop. And it does this by duplicating that check up above the loop to basically check if the first iteration of the loop needs to execute or not. So this tends to be a great optimization for performance. Not only have you eliminated one unconditional branch from the loop, but you put the loop in a form that both compilers and the hardware are well tuned for. But it does come with some code size costs, right? You have to duplicate that loop termination condition, and depending on the complexity of that condition, it will affect how much code you duplicate and what exactly the code size cost is. Well, it turns out that there's an existing threshold in LLVM that will basically set your tolerance for how much code duplication you're willing to do and still do this optimization. And we found that by tweaking that threshold, we could get a good code size savings. Specifically, if we set the threshold to 2, which is basically what you set it to in order to catch very simple loop structures like the one on this slide, but virtually nothing more complicated, that you get a code size savings of 0.75%. And we found this to be a good code size performance trade-off, specifically for Quark. The bigger core out-of-order machines tend to like loop rotation optimization more. So this is one of the cases where we did decide to do something specifically for Quark. This is not yet in trunk, and that's because some of the Quark enabling chain sets haven't yet gone in, but eventually we plan to check this in and make it specific for Quark. And I guess Zia will take over from here.
Thank you, Dave. All right, so diving right into the next optimization that we did, specifically the optimization we did to try to compact the x86 call frame. To illustrate this, I have a simple call sequence here that stores 4 arguments onto the stack and calls printf. So the typical way this is done is that we have a pre-allocated amount of space on the stack reserved for outgoing arguments, and then we simply store whatever arguments that we want into the stack before doing the call. In this case, we're storing 3 byte immediates and an address, and then doing the print. Now, this works pretty well. Is kind of performance efficient, except for, as you can see, those stores, especially the byte immediates, take up a fair bit of space. And in this case, this call sequence takes 36 bytes of encoding space. And we can do better than that. And some of you may have seen call sequences that are done with, with pushes. And as you can see immediately with pushes encode a lot smaller than stores do, especially when you have pushes of byte immediates. So you're going from an 8-byte store of an immediate to just 2 bytes. So it's kind of a clear win. You're about halving the size of this call sequence. Now, the pushes do come with a slight performance impact. Specifically, as you can see right away here, you need an additional instruction to clean up the stack to compensate for the implicit stack decrements that the pushes do. And then the other potential risk is a little bit more subtle, and that's an architectural complexity that the pushes come with that requires a little extra decoding complexity and scheduling complexity that I can discuss later for anyone interested. But in our experience with these push sequences is that we've seen very minimal performance impact on them, and they're generally a pretty big win. And in our tests for our workloads, we saw a very nice 4.2% code size reduction in size. We do expect this to be also better for non-MCU targets because MCU passes arguments and registers, and the more arguments you pass in on the stack, the better, the more savings you'll see. These changes have been committed to the trunk, although they're only enabled under OS, but we see no reason why these shouldn't be enabled for O2, and that's work that we're going to follow up on in the future. Okay, so next, stack layout optimization. So this is the work that we did to try to order local symbol tables on the stack to try to maximize the number of 0 and 1 byte offsets. To illustrate this, I have a simple x86 stack frame. So what we have on the stack is a return address, a bunch of other stuff like saved registers, and at some point we have dedicated amount of space that's given to contain all the local symbols, which could include space for spell slots, for example, or any other local variables that require space. This particular example is using an ESP-based frame, although this optimization also works for AVP-based frames. So what does an access off of this kind of a stack look like? So a local symbol that happens to be at the bottom of the stack is encoded using 3 bytes for a simple load. Well, that's not too bad. We have no offset there. All additional local variables that appear above this are going to need an extra byte to encode the offset relative to ESP. So we're up at 4 bytes, still not too bad. But once we cross the signed byte threshold, so anything above 128, things start getting a little more ugly. And now we're needing a whole 4 bytes to encode the offset. So we're now at 7 bytes for a simple load. And as you can kind of see, depending on how many variables you have and the size and the frequency access, you can dramatically affect your code size. So like a typical example is, let's say you have a big array. and that array happens to get allocated to the bottom of the stack, and then you have potentially a whole bunch of frequently accessed smaller variables, and they get allocated above this big array, then you're stuck with a whole bunch of really big, ugly encodings for all of those arrays. So what we did was we just created a simple algorithm to order these symbols based on frequency of access and size. And we found that we got a very nice 1.2% code size reduction by doing this. These changes have been committed to trunk, and they're enabled under OS and O2. OK, next, fixing excessive duplicates of immediates. So as you saw in some of the previous examples, immediates can be pretty ugly to encode. In this case, a simple store of the immediate 3 takes 10 bytes. Well, sometimes you just really have to store an immediate to memory, and there's not much you can do about this. But what if you have another store of the same immediate to a different memory location? So picture like a memset where you're copying a bunch of immediates to the to memory or the stack or whatever. Then we can maybe do something about this. Specifically, at the cost of an extra instruction to store the immediate in temporary register for 5 bytes, then we can do the cheaper encoding of register to memory at 5 bytes each. And in this example, we just save 5 bytes to store these immediates. And the more duplicate immediates you have, obviously, the more savings you get. This, again, does have a slight performance risk, and that is that you're increasing memory pressure, causing potentially extra spills and reloads in some cases, which is why we actually only implemented this in the local basic block scope. We found that the performance was minimally impacted for local basic blocks, in contrast to us also trying this on a global scope, also across basic blocks, where we saw some significant performance regressions. So, but there is still potential for additional code size there, but it just needs to be tuned a little bit more, and that's a follow-up work that we're going to do. So this gave us a nice 1.5% code size reduction. It's checked into trunk, and it's only enabled under OS, and again, we hope to port this over to O2 also. So given the length of this talk, we didn't have time to cover everything, so we just have a little miscellaneous optimization slide here where I'll just quickly mention some of the other stuff we worked on. We did do some inline heuristics tuning where we played around with thresholds and other heuristics. And we also did some LEA optimizations. We found that by eliminating, we could eliminate some LEAs and do some address propagation to reduce code size, and we can talk about those later should anyone care. Those gave us about another 1 point something odd code size reduction. Okay, so we're kind of running out of time, so I'm going to kind of speed up a little bit. So going back to code size results, as Dave said, for our D2000 target, we saw some pretty nice gains, going from 12% to being within 1% of GCC. That's really great, but for, not all of you care about D2000. Well, I'm guessing none of you care about D2000. And you might be asking, well, how does this affect just general -OS code size, which some of you might care about? Well, we tried to do our whole workload with -OS only, so no D2000 specific targets. So this is just generic 32-bit OS compilation. The GCC size dropped a little bit, presumably because we don't need to do all of the soft-float calls, and we have x87. The LLVM size did not drop. We don't know why yet. We plan on following up on this. Given that it didn't drop, we have a GCC is now 21% greater than, LLVM is now 21% greater than GCC, but the 11% or so drop that we saw with our D2000 target carried over with -OS, and it applied, so bringing the code size down to be within 10%. So as you can see, the code size savings were nice, and we actually got some good positive feedback from the community to tell us that we were actually affecting real-life applications too, and not just SPEC. And there's a quote there by Hans. Hans, thanks for letting us quote you. This is some improvements that we saw from just one of our change sets. So another question you might be asking is, okay, great. Well, code size is all great, but how did you affect performance? Well, to simply summarize this in a couple of bullets, we really didn't. Our MCU benchmarks that we ran didn't show any regressions. There were a couple of small speedups. And we also did a big core performance benchmark on an Ivy bridge on our workload, and we didn't see any performance regressions there. Well, significant ones under over 1%. And again, we did get some positive feedback from the community for performance, and here's a quote from Sean. Sean, thanks for letting us quote you, where he saw some nice speed-ups in one of his workloads. So to be fair, we are still following up on one performance regression that was filed against one of our changes under 03 FLTO. We thought we'd mention that, so this isn't all just super peachy. But overall, we felt that we'd made some pretty decent code size impacts with minimal, code size reduction impacts with minimal performance downside. So that is about all we're going to talk about for what we did. Now is a quick slide to talk about what we plan on doing to follow up. As I mentioned earlier, there's some optimizations that we still plan on tuning before we upstream, specifically the inlining stuff, and Dave mentioned the loop unrolling changes. Again, as we mentioned, there are some optimizations that we only put under OS that we feel should also be under O2, so we plan on moving those so that more people can see the impact. As I mentioned, we were not sure why LLVM was so large for simple -OS, so we plan on following up on that. And also, we documented a whole bunch of other findings that we'd like to explore. And here, we mentioned 3 of the significant ones. So there's existing code out there that tries to merge identical or near identical functions. We plan on playing around with that. We already did a little bit. There are some opportunities we found by being able to tune frame pointer elimination. And finally, we've also seen some opportunities in the way memset and memcopy get lowered or re-rolled that can help code size. And that is it.
Okay, thanks, Zia. Thanks, Dave. We've got between 5 and 10 minutes for questions.
Okay, thank you.
First of all, thanks for doing this. Every time we import a new LLVM into FreeBSD, the people responsible for the bootloader try and hit me because suddenly we have to remove features from the bootloader because it no longer fits in the available space. So maybe the next release, I will have no bruises. On the stack frame optimizations, I wondered if you'd looked at introducing a biased stack pointer along the lines of the Spark ABI, because that would free you up another 127 bytes that you can access with the single byte immediate.
So if I understood the question right, you're asking whether we've thought about introducing a second pointer somewhere in the middle of the stack?
Or just moving the stack
pointer. Or just moving the stack
pointer
up.
I think on x86, the red zone is 128 bytes. So if you bias the stack pointer, you still have enough space that you can use the before and after. You can still use the bit after the stack pointer.
Right. No, we haven't actually done any work on that yet, but it's an idea that we've thought about. Specifically, you can also introduce additional pointers into the stack, depending on how many registers you have free or how much you're willing to pay for it to get additional code size. But that's a good follow-up thing to work on, thank you.
Synopsis. Did you actually try to tune heuristics on higher level optimizations like loop strength reduction, whatever, those default values that are with OS, whether it's sufficient for your new target?
Let's see, I'm trying to think of what we did try to tune. We did try to tune loop rotation. We talked about that. And we worked on inlining because that was an obvious one. We didn't go through and turn all the possible knobs that you can turn for LLVM, but just the ones that were maybe most obvious for code size.
given the big size that we started off with, there was a lot of things that we could immediately do. But there's a lot more to follow up on, obviously.
Have you paid attention to debug information changes that might happen because of the new optimizations?
Yeah, that's a good question. So I guess the answer is yes. And that has been a point of, I guess, bugs in some of the optimizations that we did. So specifically, the call frame optimization involves having to change the CFI information is the term that's used in LLVM. It's basically describing the call stack so that you can do unwinding and whatnot. But yes, that's definitely a point of concern. We want to make sure that we're preserving that as we do whatever optimizations that we're doing. And that's a consideration that would need to be made if we were to do that stack frame biasing type of thing. We have to make sure we preserve the ability to unwind the stack. Yeah, it's definitely an important thing.
Yeah, so some of the things I've tried in the past are using, well, particularly the EBP has an SIB byte extra if you're doing accessing so it's often worth making an EBP-based stack frame just to eliminate that extra byte in multiple occurrences. And another thing we looked at using the STOS and LDOS instructions to, if you've got sequential stores and loads, you can use sort of single byte instructions to do those. But that comes at a bit of a microcode penalty.
Right. Yeah, we did, and this is something we didn't talk about much, but we have a certain class of optimizations that we came up with that were not performance friendly, and we did actually check some of those in under OZ. We tried to impact OS as little as we could. So things like introducing microcoded instructions, for example, probably wouldn't make the cut, at least for us, for OS. But yeah, we do have several documented things, not specifically the STOS instruction, but that we hope to get under OZ, and some of which we already have.
And yeah, just to say a word about the stack and frame pointer optimization. Yes, you can often save a byte by using the base pointer, but there's a big trade-off to be made there. So you don't always positively impact code size because you swiped a register from the register allocator. So you end up, in some cases, adding more spill code. And so it's just a tricky trade-off. And there's definitely opportunities there, but that's one of the things that I was referring to when I talked about picking the things that are high ROI. So that's probably higher effort to find a good tuning for it.
If I'm permitted another question, or observation anyway, another thing I'd looked at considerably too was constant generation, again to avoid the sort of four byte groups, and modifying existing constants often to make a new constant is, so if you've got a register that contains the number 100 and you want 120 or something, then often you can do that very cheaply. Constants tend to be incrementing. That's another sort of theme of constants. And generating floating point constants often is quite quick as well. So you can do things like using an LAA instruction to modify an existing constant to generate a new one more quickly than loading a 4-byte constant.
Let me take it. So actually, that's very related to one of the optimizations that Zia very just briefly touched on with the LEA optimization. That's exactly what it does. It picks existing LEAs, and if there are other LEAs that just vary by a constant, it will utilize the existing value. But we didn't really explore just pure immediates, yeah.
Well, right. I think the only time we ever see that is creating a 1, XOR it, and we increment it.
Yeah.
But we don't. But if it's already used by someone else, we won't mess with it. But that's an interesting idea.
Yeah, that's an OZ optimization.
That's an OZ optimization. Well, was. But will be again soon.
Okay, let's thank Dave and Zia again. Thanks very much.
Thank you.